Welcome back student to our complex analysis course, which is in the mathematical method course is one of the major part we are dealing with. So, in the last class I mentioned something interesting that Z1 greater than Z2, it is a meaningless sentence or meaningless expression. Z1 greater than Z2 with a mod sign is a meaningful expression. This is a meaningless because I am comparing two points. Here I am comparing two lengths, which is justified. So, now let me show you the geometric representation. So, geometric representation of a complex number. So, geometric representation of a complex number. What is the meaning of geometric representation? In the very first class I mentioned that I have a line which I call the real axis, over which all the real quantities are there. This is 0 and this is positive, this is negative, all the quantities are there. Now, I find x square plus 1 equal to 0, this kind of solution, the solution of these things do not have any real solution. So, the solution I find something which I call imaginary. So, now the imaginary numbers, if the imaginary numbers are there, then we need to put this imaginary number somewhere here, but it should not be in the real axis, it should be somewhere else. So, for that, for them we need to find another axis which is perpendicular to the real axis, and this is your imaginary axis. If I say this is my 1, this is my 2, this is my 3, this is my minus 1, this is my minus 2, this is my minus 3 and so on, then in this side I should write this is my I, this is my 2I, this is my 3I and so on. In the downwards I have minus I, minus 2I, minus 3I and so on. So, now the things are clear. If I have one number 1, if I multiply that with another quantity I, essentially I am having this point going to this point. So, that means a 90-degree rotation is there somewhere. Then this point again I multiply with I will have minus 1. That means this point again have a 90-degree rotation and I am coming back to minus 1 point. Again I am multiplying this minus 1 with a I, and when I multiply these things, then I will have a minus I. That means I am again rotating 90 degree and come to this point. Let me use another color, this point. Again I multiply this minus I, this quantity with I will have 1. So, I will return back my original position, which is here. So, that means by multiplying a real number with some number which is complex, which is totally imaginary, is eventually I am rotating this point from here to here and then here to here and here to here. I can see that. So, I have a real number and just multiply with I or 2I or 5I, whatever I like. What we are doing, we are putting this point or rotating this point somewhere here. For example, 2 is here, if I multiply with 3I, then I have 6I. It is not a rotation, it will be like this. So, the point is changing, there is something which is changing the angle also. So, that means angle is something which is important, that for the timing we should note, but there is more on that. So, let me now represent a purely complex number. Complex number is something which has a real and imaginary component together. Okay, this is I, this is minus I, this is 1. So, now any number, complex number z, which is say x plus iy, where x and y both are real, can be placed in this complex plane. This is called the complex plane. Real axis in along x and imaginary axis is along y. So, entire plane is complex plane, and all the points, each individual points are the point in the complex plane. So, if I write, say I want to find out what is the value of z is equal to 3 plus 2i, x value is 3, I need to go to 3, 1, 2, 3, and y value is 2. So, the point is here. So, this is the point. So, z is essentially gives me a point, that is the thing last class we mentioned. This is the thing which is giving you the point. Now, I want to find out another point, this is z1, another point z2, which is say 2 minus I. Okay, this is also another point. Where the point locates? It is 2, 1, 2 and 1 in the downstairs, because it is minus I. So, somewhere here. So, the point is here. So, z1 and z2 are merely representing 2 points in the complex plane, that is all. It is not more than that. It is just 2 points which are representing 2 things in 2 points in the plane. Now, if I want to say that z1 is greater than z2, that I mentioned in the last class, that obviously meaningless, because this point and this point are just merely point. But now I am, if I say mod of z1 is greater than mod of z2, that is meaningful. That is meaningful. Why? Because mod of z1 is nothing but the length of these things from 0. This is your mod of z1. What about mod of z2? Mod of z2 is also the length of these things. So, how I calculate the length? We know that if it is, this value is 3, this value is 2, the length is nothing but 3 square plus 2 square root over of that. So, it is nothing but z3 is nothing but 3 square plus 2 square whole to the power half, which is, by the way, is the norm of this quantity, the mod of this quantity. So, mod of z1 we know by formula, it is root over of x1 square plus y1 square. If it is represented by x1 and y1, then it is here, it is nothing but 3 square plus 2 square to the power that. So, that means 9 plus 5 whole to the power of half. In the similar way, we have this quantity, this length is nothing but this mod of these things, which is this length, and this length is 2 square plus 1 square whole to the power half root over of 5. So, here I have something and here I have something. Now, I am saying that mod of z1 is greater than z2, because it is giving you the length of these two points. Okay. So, now I understand what is the meaning of these things. Now, few interesting things of that. I have 2 points, these and these. So, it seems to be a vector like thing. So, now I want to find out z3, which is the addition of these two quantity z1 plus z2. So, I know the addition formula, z1 is 3 plus 2i and Z2 is 2 minus I. So, that means it is something 6 3 plus 2 sorry 5 and then plus 1, that means 5 plus I. So, if I put this 5 plus I, it will be somewhere some point in here, and how we are grading these things. So, it is basically the vector rule we are having. So, vector rule suggests that if I add these two quantity like one vector plus another vector, I will generate another vector. So, let me do that like this. So, I need to extend this to find out where the point should locate. It is 4, it is 5. So, if I make a parallelogram to this quantity, my scaling is not correct, but if it is correct, then it should be somewhere here, and if I add these two things, this is a vector parallelogram. So, 5 plus I is somewhere here, 5 and this is I. So, my addition of two things give me another point, which is this is my Z3. But Z3, as I mentioned, this is the addition of Z1 and Z2. Z1 is this, Z2 is this. If I consider these two as a vector, then this is nothing but the vector addition of these two quantity. It is nothing but the vector addition of this quantity. So, this quantity red line is basically gives you this point, and this red line is basically gives you mod of Z3, the length of these things. So, addition of two quantity in this plane, addition of two complex quantity in this complex plane is nothing but, if I consider these as a vector, this as a vector, and if I add these two vectors separately, I will have a resultant vector. It is something like the resultant vector, which is given by this Z3, and from 0 to Z3, if I join, the length of this line is basically the norm or the mod value of this quantity. So, from this we can now say one important thing. If Z1 and Z2 is this, if I want to find out what is the relationship between mod of Z1 and these things, so mod of Z1 is equal to mod of Z1 plus mod of Z2, this. Now, we know that this is the third angle, this is 1, this length and this length are same. So, from here we can have one important identity, mod of Z1 plus mod of Z2 will be always less equal to, sorry, always greater equal to mod of Z1 plus Z2. Mod of Z1 plus Z2 is nothing but Z3, which is the sum of these two. So, these two are, if I make a mod of these things, it will be always be less than whatever, and this is nothing but the triangular law. So, you know the triangular law, two sides is add up two sides is always greater than the third side in a triangle. So, here we are using these two, and this is a very well known law in complex analysis. Okay. In the similar way, I can, let me erase this because I believe you now understand the entire concept of these two. With this, we can also write a general form, Z1 plus Z2 plus Zn is always less equal to mod of Z1 plus mod of Z2 plus mod of Zn in general. In the same way, if I trying to add, this is my one vector, this is my another vector, this is my another vector, and if I add these two vector resultant vector, so this plus this always be greater than this. Okay. Now, the next thing is that so far we are dealing with the complex numbers, and these complex numbers are represented in Cartesian coordinate. So, Z is represented by x plus iy. In Cartesian coordinate, I am representing that, and also we find that this is my real axis, this is my imaginary axis, and Z I represent like x plus iy. So, some point here, this is my x, this is my y, so somewhere here. So, this point is my xy, which I represented like x plus iy, and this is my Cartesian coordinate. Now, we can also write the entire thing in different coordinate system, which is polar. So, we call it a polar form. What I need to define to define this point, which thing I need? First thing is the coordinate, which is here x and here y. So, once the coordinate is given to you in the Cartesian form, you readily understand which point you are talking about, and this point is nothing but the complex number. Now, what I try to do, that I try to define the same point in different coordinate system, and here my coordinate system is polar. So, if I have this angle theta and this r here, then I can also write these things. What should be the coordinate of this? I should write it as r theta. This is a different coordinate, polar coordinate. In the polar coordinate, I also write these things. Now, if I write r theta, readily you can understand there is a relationship between r and theta and x and y, and we know that very well. So, r is nothing but x square plus y square whole to the power half. It has to be, because r is the length of this number. So, if this is my z, which is x and y, so r is nothing but the mod of z, so which is equal to mod of z. Okay. What about theta? Theta also we know, because I know this is x, I know this is y. So, if x and y is known to me, then what I can do? I can do tan theta is y by x. So, theta is tan inverse of y by x. So, I have r in form of x and y, I have theta in form of x and y, and if I have r and theta in my hand, I can readily write this into another coordinate system, r and theta. But apart from that, I can write these things in a different way, not in a different way, but let me now replace this x and y in terms of r and theta. My goal is to write z in terms of here z. When I write z, I should write it here, z is a function of x and y, right. I need to write z, which is a function of r and theta. How to write that? So, now my x has to be replaced and y has to be replaced in terms of r and theta, in terms of r and theta. So, from here I know that sin theta is how much? This divided by y divided by r cos theta. How I define cos theta? X divided by r. So, my y is essentially r of sin theta and my x is essentially r of cos theta. So, now I can write my x and y in terms of r and theta and r and theta. Once I do that, then I can readily write this as r cos theta plus I sin theta. So, I define the same point in terms of x y, which is coordinate system, but apart from that I can also write this in a different way, which is cos theta plus I sin theta. After having that, let me now erase this. Hopefully you understand what is the geometry. A beautiful thing comes to our hand. So, now I defined a complex number in a complex plane with x and y and an r and theta, which is defined in this way. So, let me do one thing. So, what is e to the power theta? Expansion of e to the power theta is 1 plus theta by factorial 1 plus theta by factorial 2 plus theta square theta cube by factorial 3 plus theta to the power 4 by factorial 4 plus theta to the power 5 by factorial 5 and so on. This is the expression of e to the power theta. What is the expression of sin theta? Which is theta minus theta cube by factorial 3 plus theta 5 by factorial 5 minus theta 7 by factorial 7 and so on. Only the odd numbers with changing sign. Cos theta is 1 cos theta is 1 minus theta square by factorial 2 plus theta to the power 4 by factorial 4 minus so on. Even term, even power with changing sign. Now, once I have sin theta and cos theta in our hand, then readily I can put one thing, that if I put e to the power I theta instead of theta, then this expression is slightly changed and it will be theta e to the power I theta is 1 plus I theta by factorial 1 minus theta square by factorial 2, because theta square there is a minus, because in place of theta I am putting I theta and then I make a square of that. So, minus sign will be because of that I, then minus of I of theta cube by factorial 3, this term will be plus of theta to the power 4 factorial 4, this term will be plus I theta to the power 5 by factorial 5 and so on. Now, if I look very carefully to this term, one, this thing, these things, all the terms which are associated with even powers, if I take this term aside, I will have one series. And what about this theta and this theta which is associated with the odd powers? So, what I will do that I will take I common of that. If I take I common, then I have theta factorial 1 plus minus theta cube factorial 3 plus theta to the power 5 factorial 5 and so on. So, it is like a miracle, we have one series which is cos and one series which is sine just multiplied by I. So, this is cos theta plus I sin theta. So, e to the power I theta is nothing but cos theta plus I sin theta, which I show you meticulously, which is called the Euler's formula, which is a famous formula. And if I use this Euler's formula, then the point can be represented in a more compact way in polar coordinate. So, this quantity if I write in polar coordinate again with r theta, it is r cos theta plus I sin theta. We know that e to the power I theta is cos theta plus I sin theta. I will just replace this cos theta plus I sin theta to e to the power I theta. So, r e to the power I theta is the representation of a complex number in the polar form, and very compact form, very useful form, and this is something which gives you many interesting ideas, and we will go to this. For example, if I multiply two quantities Z1 and Z2, so basically it is e to the power r e to the power I theta 1 multiplied by r 2 e to the power I theta 2. If I do that, then I can write it as r1 r2 e to the power of I theta 1 plus theta 2. Essentially, what is the meaning of that? R1 and R2 if I write big R, and theta 1 and theta 2 if I write big phi. So, my new after multiplication I have a new number, new complex number, I call it Z3. So, Z3 is now represented in polar form, but the interesting thing is that here we have one angle, here we have another angle. So, two points are like this. This is my Z1, this is my Z2. This point is R1 theta 1 and this point is R2 theta 2. When I multiply these two things, these two quantity, then we have another quantity whose amplitude is R1 multiplied by R2, something bigger than that, and not only that, the angle is this angle plus this angle. So, I will have something here at this point after making the multiplication of these two quantity. So, apart from that, there are many interesting things that we will find in the next class, where we do many things with this form. We need to find out for example, the square root of some complex number, how to find out the square root of this complex number using this particular form. We will learn that, but the concept is very nice, that you can represent a complex point in a complex number in complex plane in terms of x and y, which is convenient, but also you can do the same thing by putting the point in these things, and you will find more information, and we can extract more information with this form, and that is also equally important and give you much more interesting aspects of complex number, and we will learn that in detail in the next class. So, with that, so let us stop this class today here. In the next class, we start with this geometric representation and this polar representation, and find out many interesting things which is related to complex analysis, and will be helpful for you to understand the complex analysis or complex points in a more convenient way. So, with that, let us stop here. Thank you for your attention. So, see you in the next class.